Okay, so we're going to start with igneous rocks and volcanoes. Why should we study igneous rocks? So here are some examples. So here's a volcano. You have lots of people around the world who actually live near volcanoes. You have here some gravel made of igneous rocks. Igneous rocks are very hard in most cases. They're very hard. So they make good construction materials like this retaining wall here, or like I said, the gravel. Or here is a countertop made of igneous rocks. Here is an arrowhead made of an igneous rock called obsidian. Also, some surgical scalpels are made of obsidian because obsidian is natural glass and it's able to be carved in such a way to be extremely sharp. And then also we have statues, and also here's Mount Rushmore. That was carved into an igneous rock called granite. The whole mountain here is made of granite. So what is an igneous rock? Igneous rocks are rocks that form from the cooling and solidification of molten rock. Igneous rocks can be in the form of aggregates of mineral grains or volcanic glass. So aggregates of mineral grains or crystals, an example would be granite, shown here. And you have different crystals in here. You have some pink, some white, some black. And I showed granite as a good example of this because you could see the different crystals because they're different colors. There were other igneous rocks where you can't really see the different crystals as easily. And then volcanic glass, for example, obsidian, actually contains no crystals at all. And we'll discuss that later. So what is molten rock? Again, igneous rocks form from the cooling and solidification of molten rock. So what is molten rock? Molten rock is melted rock. It's basically just rock that is in the melted fluid form. So that can be in the form of magma, which is molten rock below the Earth's surface, or lava, which is magma that reaches the Earth's surface. In other words, erupted from a volcano. And then we just have some examples of the temperatures that lava could form at. And magma is hotter than lava because it's beneath the surface. It's more insulated by the interior of the Earth. So how do solid rocks melt? So as a solid rock is heated, the atoms move around within the rock at increasing speeds. When the energy of motion of the atoms is greater than the energy that holds the bonds together in the crystals, then that's when the rock can melt. However, if a rock is under high pressure from overlying rock layers, it may actually not melt, even though it reaches high enough temperatures to be able to melt. It may actually not melt. So melting involves temperature, but also the ability for atoms to move around enough to break the bonds. So we'll get into that in a few minutes again. Now also, minerals in a rock do not all melt at the same temperature. And that leads us to what's called partial melting. And when you think about, let's say, ice melting, it melts at a particular temperature, 32 degrees Fahrenheit or 0 Celsius. and water freezes at the same temperature that ice melts. Okay, so that's like the freezing and melting temperature of water or ice. You have a particular temperature, 32 degrees Fahrenheit. So minerals also have particular temperatures that they melt and crystallize at. So I will give you a food example of partial melting. So you could think about chocolate chip ice cream. If you were to leave the chocolate chip ice cream on the counter, the ice cream will melt. But even though the ice cream melts, the chocolate chips will still remain solid at room temperature. So that's like partial melting, okay? Because the chocolate has a different melting temperature than the ice cream does. Okay, so that's how you achieve partial melting of chocolate chip ice cream. Now you can also melt the chocolate, but you would have to raise the temperature even further in order to be able to melt the chocolate as well. And that all of this is because you have different melting temperatures of the ice cream versus the chocolate chips. So in a rock, the minerals kind of behave the same way. So at one temperature that the rock reaches, you'll start to melt some crystals, but then some of the other crystals will need a higher temperature to melt. So that's all partial melting. That's the concept of partial melting. So where does magma come from? Most magmas come from the partial melting of the Earth's mantle. So the asthenosphere, which we talked about last class, the asthenosphere is an area below the lithosphere. And it's very hot, but it remains a solid material rather than melting, even though it's really hot. That is because the overlying pressure of all the rocks on top of the asthenosphere prevent the atoms from moving around enough to melt. So the asthenosphere is hot enough to melt, but it's under too much pressure in order to melt. Okay, so the asthenosphere would otherwise be melting if it were not for all the overlying pressure from the rocks on top of it. Mainly the lithosphere is on top of the asthenosphere. So that puts enough pressure on the asthenosphere to keep it from melting. Now, if you were to start having cracks in the lithosphere, or if the lithosphere started to become thinner for different reasons, which we'll talk about when we do plate tectonics, then you start to partially melt some of the minerals in the asthenosphere. That's called decompression melting, okay? Because you're starting to release some of the pressure that's on the asthenosphere, allowing it to start to melt. But again, partial melting is because some minerals melt at different temperatures than others. Now, you could also have partial melting if you had a rise in the temperature rather than just having like the decompression from less pressure from like a crack in the lithosphere. You may also have partial melting related to if there's a rise in the temperature. Okay, so here's the asthenosphere beneath the lithosphere, right? It's under all this pressure and that keeps it from melting, even though it's hot enough to melt. Okay, so some of the minerals in the mantle rocks will start to melt, while the rest of the asthenosphere part of the mantle remains solid. Again, that's because some minerals melt at different temperatures. Okay, so here is where the decompression melting is happening. You have some of the rocks, some of the minerals down here will start to melt. And then what happens is the melted rock material will start to rise up. And it rises because it's less dense than the surrounding solid rock. So it starts to rise up and separate from the area that it was initially. It rises up and forms what we call a magma chamber. So then you have like this blob of molten magma that's just beneath the Earth's surface. So different factors related to partial melting include the amounts of pressure that is applied to the mantle by overlying rocks. And when I say the mantle, I'm talking specifically about the asthenosphere part of the mantle. Another factor related to partial melting is the temperature. The mineral composition, because again, some minerals melt at lower temperatures and other minerals melt at higher temperatures. And actually also the water content. So any water that might be present either in the rocks or in the minerals or just in the area, because maybe we're talking about rocks in the ocean, and you may have cracks in the rocks allowing some ocean water to seep down. So the water content is going to lower the melting temperature of rocks and minerals, making it easier for those rocks and minerals to melt. So that's another factor related to partial melting. So where does the magma go after it forms? Again, I just mentioned the word magma chamber. So the molten rock can collect in the magma chamber, right? This is the magma rose up into this area closer to the Earth's surface. So that's your magma chamber. Or it can actually erupt out of a volcano. And at that point, it would be called lava. And now remember, the magma is rising because it is less dense than the surrounding rocks. This is also why a helium balloon rises in air, because helium is less dense than regular air. Anything that's less dense is going to rise. So the magma is less dense than the surrounding rocks, so it will start to rise up. Then we have the term plutons and igneous intrusions. Plutons are solid igneous bodies underground that form from the cooling and crystallization of magma. So generally this would be in a magma chamber that starts to cool and over time solidifies. That would be the formation of a pluton. Okay, so it's basically the magma in a magma chamber crystallizing and forming into a solid rock. Then that would be a pluton. Igneous intrusions are areas underground where magma has seeped into cracks or other spaces in the pre-existing rocks. And the rocks that are intruded by the magma are collectively called the country rock. So this diagram shows different types of plutons and igneous intrusions. Again, the word pluton is more related to when the rock is solid, when the magma has solidified and crystallized. That's more what a pluton is. And the igneous intrusion, usually we're talking about it being related to molten rock that hasn't necessarily cooled and hardened yet. Okay, so let me zoom in to this picture here. So the rock underground, all these rock layers, this all collectively called the country rock. And then here's a magma chamber. And then some of the magma has seeped upwards in through different cracks and spaces in the rock. And then here is a pluton where the rock has already hardened and solidified. So then you have these things called sills and dikes and batholiths. So let's see what those words mean. Dikes is when magma intrudes at an angle to the country rock. Okay, and then you can see this dike is going vertically and this one is going kind of on an angle compared to the country rock, which is relatively flat layers. Okay, so these are dikes because they are at angles to the country rock. Sills are when magma intrudes parallel to the country rock layers. For example, intruding in between sedimentary layers. So the country rock layers here, and then the sill is going in between those layers pretty much parallel in the same direction that the layers are oriented. Okay, so those are sills. This would be a sill. Well, these are not parallel to the country rock layers, so those are dikes. And then a batholith is a large igneous body. So this is a batholith. Okay, and again, the country rock is the crustal rock that the magma is intruding.
I have a quick question.
Yes.
Can you define a laccolith? Because to me, it kind of resembles a sill.
Oh, let me see. Let me get you like a definition sounding answer to that. Okay, so when an intrusion starts to inject between layers but then domes upward, it is called a laccolith.
Okay, so basically a sill that creates a dome.
Yeah, so it
Okay.
it domed a little bit within that sill.
Okay, yeah, that was perfect. Definitely more simplified than textbook, I think.
Okay. Okay, so then I just have a little trick of how to remember which is a dike and which is a sill. Okay, so the word dike has the letter K in it. And when you look at the letter K, wait, that's not gonna work. When you look at the letter K, it has angles. Okay, so these angles here, right, this is going vertically, this part of the K is on an angle, this part of the K is on an angle. So the letter K represents similarly how a dike will look here, right? It goes on an angle, this part's going up and down, right? You kind of see that? So that's how you could remember the word dike is igneous intrusions that go at an angle. Now, the word sill has L's in it. And the letter L's, the letters are parallel to each other in the word. Okay, so these are two L's that are parallel to each other. And a sill is parallel to the country rock. Now, you don't have to use this as a way of remembering the two, but if it helps you, then good. Okay. So it's just like a visual mnemonic way of remembering the difference. Okay, then we have inclusions or xenoliths. So sometimes chunks of the country rock break off and then are actually incorporated into the magma without melting. And then later on, when that magma cools and solidifies and turns into a rock, you can see the inclusions in the solidified rock. So here's just a diagram of the country rock is the grayish part in this diagram. Okay, so here's the magma seeping upward. And then this piece of the country rock breaks off and gets incorporated into the magma. Here's a couple of other pieces of the country rock breaking off and getting into the magma. And then in this picture, you can see the white rock is granite, which was the intruding rock. And the black pieces of rock are the inclusions. So like this piece of rock right here is like this piece right here. And then when the whole thing solidifies, you're left with those inclusions within the pluton. Okay, and then here's another inclusion. Inclusion and xenolith is the same thing. Okay, so now let's talk about the different types of magma. So we classify magma types based on the composition, mainly referring to the percent of silica that is in the magma. So if you remember from last week, silica is silicon and oxygen. And that's what silicate minerals were composed of. So here is a list of the different magma types. You have felsic magma. That's more than 65% silica. Again, silica is silicon and oxygen. So greater than 65% silica is considered to be rich in silica. And then you also have aluminum, potassium, and sodium in a felsic magma. And usually felsic magma will eventually solidify into light colored rocks. That's how it happens, because certain minerals will give you darker colored rocks and some other minerals will give you lighter colored rocks. Mafic magma is less than 52% silica, so we consider that to be silica poor. Mafic magma is often rich in iron, magnesium, and calcium, and mafic magma usually forms dark colored rocks. Intermediate magma is a composition between felsic and mafic. Ultramafic magma is less than 45% silica. Now, I'm not going to ask you on an exam to repeat these percentages back to me. I just want you to more know that felsic is silica rich and mafic is silica poor, and then intermediate is between the two, and that ultramafic is associated with mantle rocks. Okay, so the mantle is ultramafic. And those rocks are usually black and green, and the rock type is usually called peridotite, or most of the magma is made up of this rock called peridotite. The first lecture has information also talking about peridotite, and I think I had a photo of peridotite in there. Are these different from felsic lava and mafic lava? These are the same, it's just that felsic magma would be underground and felsic lava would be above ground. So then here's the same information, but I put it in a chart form. Okay, so here's your magma types and your silica content. And then this is a list of other components that make up magma or lava. Okay, magma is pretty much the same as lava. It's just that magma is found underground and lava is at the surface. Okay, so most magma is going to contain silica. And then other constituents include aluminum, calcium, sodium, iron, magnesium, and potassium.
Professor, I have a question.
Yes.
The reason why I asked that is because on the review sheet, you want us to compare the viscosity of mafic lava. So do you just want us to put that definition that you have of magma or no?
Okay, so we did not actually get up to that particular question yet.
Oh, okay, okay.
I figured that's why you were asking the question though. Because yeah, there is a question in the review sheet, but we did not get up to the answer yet.
Okay, thank you.
You're welcome. So here are some characteristics of magma. We're going to start with viscosity. Viscosity is the resistance to flow. In other words, does the fluid flow easily or does it not flow easily? So here are some examples. A high viscosity liquid would be like honey, toothpaste, or caramel. So those do not flow easily. A low viscosity liquid would be like water, so it flows easily. So what factors may affect viscosity? Temperature, silica content, and dissolved gases. So higher temperature is going to reduce viscosity. So hotter magma or lava is going to flow more easily than cooler magma or lava. And a food example would be like cold olive oil or cold coconut oil, which actually turns into more of a solid material, but it's not like really solid, versus warm oil, which flows more easily, okay? You'll notice a lot of my examples for geology actually are food examples. Okay, so if you've ever seen coconut oil or olive oil, when they're cold, they don't flow as easily, but when they're warmer, they will flow more easily. Okay, so temperature will affect viscosity. Increasing silica content increases viscosity. So mafic lava or magma has less silica and is going to be more fluid. Felsic lava or magma has more silica and is going to be more viscous. So mafic lava flows more easily. felsic lava does not flow as easily. So that probably answers the question in the review sheet pretty completely. But when we get towards the volcanoes part of this lecture, I will also mention this related to volcanoes as well. Okay, and also I'll just add in here magma just to make it more clear that these are interchangeable. Lava and magma in the discussion of viscosity is pretty interchangeable when you're comparing mafic to felsic. Okay, and then higher amounts of dissolved gases will also reduce viscosity. So if your lava or magma has a lot of gases dissolved in it, it'll actually flow more easily. Okay, so all of that was referring to, everything we've discussed just now was referring to magma and lava and why rocks will melt and what happens to melted rock. So now we're gonna go from that and go the other direction and discuss what happens if melted rock cools and how igneous rocks form from melted rock. So it's like opposite of what we were just talking about. So when melted rock or molten rock cools, it can become an igneous rock. So magma, which is less dense than the surrounding solid rock, may rise closer to the Earth's surface. And then because it is further from the heat of the Earth's interior, it will start to lose heat and cool. So that brings us back a little bit to, let's say, this diagram here. So the magma lower down is hot and it's insulated by all the surrounding rock and it's deep underground. But as that magma rises, it's getting closer to the Earth's surface and further from being insulated and further from the heat of the Earth's interior. So as it goes closer to the surface, it's able to cool off a little bit more, and that's when it'll start to turn into an igneous rock, when it cools. Okay, that's how the rocks form. The molten rock cools. So as it cools, the molten rock will lose energy and the atoms in the magma will slow down and start to bond together and crystallize. And this forms small nuclei of solid minerals. And again, when I'm saying the word magma, in this case, we can also replace it with the word lava. Okay, it's more just molten rock. So here on the left are some random atoms in magma or lava. And then the magma or lava that these atoms are in is starting to lose heat and cool down. So when a material cools, the atoms are not like moving around as much. Excuse me. So then what happens is the atoms are going to start to bond with each other. Now this is a hypothetical bonding situation, okay? I just made up that these atoms bonded in this shape. Okay, these are just hypothetical atoms. But they start to bond together, and we talked last week about why atoms like to bond with each other. One of the reasons was related to the covalent bonding, because the atoms are trying to fill their outer shells. That was one of the reasons why atoms were bonding together, okay? To fill their outer shells, for example. So in this case, the atoms bonded together, and this is a crystal, okay? They form a crystal in a particular shape. So once you have one crystal that forms, the rest of the atoms are going to start to bond onto that crystal that formed. So we call this a nucleus. It's a nucleus, but like plural, it's nuclei, more than one. So I'll show you how that works. So once you have one nucleus, other nearby atoms or ions are going to attach onto that nucleus. And then you will form a repetitive geometric pattern or a crystal structure that's repeated over and over again. So the atoms are going to continue to grow outward. And then you get what's called an interlocking texture or interlocking crystals. So nearby nuclei that are also forming will grow outward until the mineral grains bump into each other. This results in an interlocking texture. Okay, so the mineral crystals grow outward until they bump into neighboring crystals. Just like that. Okay, so you see, I'll show you again because it's fun, right? They're growing outward until they bump into each other. Okay, and then eventually you would get all around this area within the magma, you would also have other crystals growing, and they all grow outward until they bump into each other, and that forms an interlocking texture. Okay, and in this case, an example would be granite. Okay, where you have different crystals that grew until they bumped into each other. And then here is just a list of common felsic minerals that form in igneous rocks: coarse, potassium feldspar, muscovite mica. These are minerals that are light in color. And then common mafic minerals in igneous rocks include olivine, pyroxene, which is also called augite, amphibole, which is also called hornblende, and biotite mica. And these are dark in color. So when we go back to the granite, the pink is feldspar. Some of the dark is going to be your hornblende and your pyroxene, for example. We're going to go more into these minerals during lab though, and then you'll see more pictures of them. So there were two types of settings where molten rock can cool and form igneous rocks. So you see on the left, everything is still molten, and on the right, everything is solidified and turned into rock. So you see on the left, you have magma chambers, you have laccolith, you have sills, dikes. And then above you have volcanoes. Here's a couple of volcanoes with some lava. So if magma cools beneath the surface, it forms what's called an intrusive igneous rock. We also call those plutonic. That's your most common igneous rock type. If magma erupts at the Earth's surface as lava, it forms an extrusive igneous rock or a volcanic rock. Okay, so everything on top of the Earth's surface or at the Earth's surface is a volcanic or extrusive rock, and all of this down here is an intrusive or plutonic. Okay, and in this case, on the right, these areas of magma have all hardened and turned into rock. And on the surface, they've all turned into rocks, all the lava. Okay, and that's what we call a pluton, which I mentioned earlier. And a rock type that this might have formed would be granite. The cooling and crystallization process can take thousands of years to form the pluton. Let's just add for plutonic rocks specifically, because for volcanic rocks, it's not going to take thousands of years to cool and crystallize. And this is just a summary of what we're talking about. Intrusive versus extrusive. The extrusive is shown by this bracket here. It says extrusive realm. That's your volcanic area above or at the surface. And then your intrusive realm is everything that's beneath the surface, okay, including inside the volcano. While this molten rock is inside the volcano, it's still intrusive. And then here's a summary, excuse me, intrusive versus extrusive. So intrusive igneous rocks, the magma takes a long time to cool beneath the Earth's surface because it is insulated by the surrounding country rock. This is similar to how hot coffee in a styrofoam cup will stay hot for a long time because the styrofoam is insulating the coffee. So the country rock, we could just go back here, the country rock around the magma is keeping the magma hot for a longer period of time than, let's say, the lava flow, which is exposed to the air. So it's able to lose heat a lot faster. So because it takes such a long time for magma to cool, your crystals are actually able to grow and form visibly, like they form visible crystals. Sorry, the rock is gonna form visible crystals. Okay, now we're talking about large crystals or visible crystals related to slow cooling. So let me just give you an example. Again, the same granite that I showed you before. So this granite here, you could see the different crystals. Those took a long time to grow, but because this rock cooled slowly, the crystals were able to form large enough to be visible. Okay, so your example would be granite, right? Granite. In contrast, when you're talking about extrusive igneous rocks, the lava erupts at the Earth's surface and will cool quickly because at that point, the lava is exposed to air or actually water as well if we're talking about a volcano underwater. And the air or the water is a lot cooler than the temperature of the lava. So the lava loses heat quickly, and the crystals do not have a lot of time to grow before the lava solidifies. So you either get very small crystals or no crystals at all. If you get no crystals at all, that's volcanic glass. So to summarize, fast cooling, you will find tiny crystals or no crystals at all. And that is glass. So basalt or obsidian are your examples there. And then again, slow cooling, you get crystals that are able to grow and they will be visible. Now, a little bit later in the lecture, I have pictures of different rock types. So you'll see like what a basalt, obsidian, and granite look like. I did show you granite already. Obsidian I showed you at the very beginning of the lecture as well, but we'll look at these again. So here's another question then. Why are there areas where intrusive or plutonic igneous rocks like granite are at the Earth's surface if those rocks form deep within the Earth? So let's just go back here. Here's granite, which formed very deep underground, right? Granite. But then you go to areas like Mount Rushmore, where it's granite sitting at the Earth's surface in a mountain. Or here, I took this picture at the top of a mountain called Old Rag. That's a mountain in Virginia in the Shenandoah region. So we're high up in a mountain and there was granite rocks at the top of the mountain. It wasn't actually the top of the mountain, it was just high up on the mountain, but it wasn't actually the top. So yeah, the question, how does the granite get at the Earth's surface if it formed deep within the Earth? So that gets us thinking, like, geology is not something that just happens. You know, rocks don't just form and then stay where they are for like billions of years. Things move around, things happen and change. So we could see ancient plutonic rock where land has been uplifted and erosion of overlying rocks has occurred. So this goes along with the diagram I showed you before. So this is like part A, this is part B, see like the letter A and B. Okay, so this is the molten rock, this is when it turns to solid rock. And then this is later on when erosion has happened and all of the overlying rocks that were covering the pluton are now eroded away. And now you're able to actually go and walk on top of this pluton. Okay, so it's uplift and erosion. The uplift happens because you have less rock on the crust pushing down into the mantle. So as you lose rock off of the crust, the crust kind of like rebounds a little bit and uplifts. So this rebounds, that's uplifting the land, and then you have continuation of the erosion. So uplift and erosion usually happen simultaneously. So then we're going to get into the order of mineral crystallization and melting. And this is called the Bowen's reaction series. So the temperatures at which specific minerals melt and crystallize are shown on the Bowen's reaction series. So remember, partial melting occurs because different minerals have different melting temperatures. The same goes for crystallization of minerals forming in magma. So melting and crystallization are opposite, but it's going to occur at the same temperatures for specific minerals. Crystallization temperatures therefore equal the melting temperatures, just like water and ice. So water freezes at 32 degrees Fahrenheit and ice melts at 32 degrees Fahrenheit. Okay, so some minerals will form and melt at a particular temperature. So mafic minerals melt and crystallize at high temperatures. Felsic minerals melt and crystallize at low temperatures. Now, when I talk about high and low, we're still talking about extremely hot temperatures, but they're low or high compared to each other. So like the felsic minerals, it's going to be related to like 800 degrees Celsius, which is still extremely hot, but it's low compared to the mafic minerals. So So the melting and crystallization temperatures for different minerals are predictable and shown on the Bowen's reaction series, which I will show you on the next slide. So at first glance, this may look pretty confusing, but we could break it down. So this is basically a graph, and it shows you at the top of the graph is 1400 degrees Celsius, and the bottom of the graph is 800 degrees Celsius. So this is the temperature. And then here you have on the right is only one particular mineral called plagioclase. Plagioclase is a type of a mineral, okay? It's a type of feldspar. So that's the continuous branch. And what that's referring to is at higher temperatures, the plagioclase will be more rich in calcium. And as temperatures get lower, the plagioclase will be more sodium rich. Okay, but that's really all I'm going to talk about right now about the plagioclase feldspar. We're going to focus mainly on this discontinuous branch on the left. So we'll start out the conversation talking about magma. Okay, so let's say we have magma. It's very, very, very hot. We start to cool the magma, and as the magma cools and reaches 1400 degrees Celsius, you start to have the atoms in the magma bond together and form a mineral called olivine. So olivine is the first mineral that's going to form as this magma cools. Now, some of the olivine crystals are going to react with the rest of the liquid magma, and you have a chemical reaction, and then you start to form some of this mineral called pyroxene or augite. So the olivine, you're going to have some olivine still there, and then you'll have some pyroxene. So when you go across, it says mafic magma. Okay, so we start out with a mafic magma. And then some of the pyroxene is going to go through a reaction with the rest of the liquid magma. Because keep in mind, you have some crystals that are solid and they're like floating within this liquid magma. So the mineral crystals, some of them are able to have like this chemical reaction with the rest of the magma. So then some of the pyroxene will form a crystal called amphibole. One particular type of amphibole is called hornblende. Okay, then some of the amphibole will have a reaction with the rest of the magma and form biotite mica. And all of this happens as the temperature of the magma continues to cool, by the way. Okay, so like as the magma continues to cool, once it reaches this temperature here, then the pyroxene will be able to form. But it's also related to a chemical reaction with the magma. Okay, so as the magma cools, cooler and cooler, you're able to form more different types of minerals. So at this point though, all of the minerals that formed before this point incorporated the iron and magnesium that was in the original magma. Okay, so all of these minerals already took up all the iron and magnesium. So at this point right here, all that you have left in the remaining magma is potassium, aluminum, and silicon and oxygen. So that's why when you look on the right, it says felsic magma, right? Types of magma, felsic, because at this point, all the solid crystals have taken up the mafic components, and you're only left with the silicon, the oxygen, the potassium, and aluminum, which is basically what a felsic magma is composed of. So then continuing to cool the magma, you're gonna form potassium feldspar, which takes up the potassium, and then you form the muscovite mica also. So both of these minerals take up the rest of the potassium and aluminum. By the time the magma cools down and reaches 800 degrees Celsius, the only component left that's still liquid magma is silicon and oxygen. All of the other components are now within crystals, within minerals that formed solid crystals. So the only thing left that didn't crystallize yet is silicon and oxygen. And that's what quartz is made of. So the last crystal to form is quartz, or the last mineral to form is quartz. That's the only thing left. Okay, so quartz forms around 800 degrees Celsius, which again is still very hot, but it's cooler than the 1400 degrees Celsius that olivine starts to crystallize at. And again, this whole thing is referring to magma that's extremely hot and then starts to cool. So we talked a little bit earlier about why magma will start to cool. Again, for example, the magma may have risen closer to the Earth's surface, further from the interior of the Earth where it's hotter. And then as it's closer to the Earth's surface, it starts to lose heat. Again, I also mentioned that the cooling of magma and the formation of plutonic rock could take thousands of years. Okay? So at this point, once you form the quartz, you really just have a solid rock underground or a pluton, and you no longer have liquid magma. Okay, and then the plagioclase works in a similar way, that as you have the magma cooling, the plagioclase incorporates more sodium than the calcium. Okay, so I'll show you on the next slide. The original mafic magma, and then as you increase your time and you decrease temperature, not increase time, as you go on in time and you decrease the temperature by cooling the magma, some of those minerals that formed are actually going to fall to the bottom of the magma chamber. That leaves the rest of the liquid magma more felsic. Okay, again, because you're removing the more mafic components and incorporating them into the solid crystals that form. Okay, and then this is just the same thing, but it's a different diagram that shows you like the crystals. Okay, so olivine, pyroxene, amphibole, biotite, potassium feldspar, muscovite, and quartz. Now, potassium feldspar is abbreviated by the letter K, which stands for potassium. So the opposite would happen if you had a rock and then melted it. So if you had a rock and you start to melt the rock, you're starting at a low temperature. The first crystals that are going to melt is the quartz, the muscovite mica, and then the feldspar. As you increase the temperature of that solid rock, then you're going to melt your biotite, the amphibole, the pyroxene, the olivine, and then also the sodium-rich plagioclase, and then later the calcium-rich plagioclase. Okay, so quartz will form at around 800 degrees, but also melt at around 800 degrees. So it works both ways. Melting a rock as a rock is heated, or forming crystals as magma cools. And this is what we'll start with the next lecture, okay? So we're gonna end with this.